is alpha decay. Alpha decay is a helium nucleus in that it has 2 protons and 2 neutrons. No electrons. It's not the helium atom, it's a helium nucleus. 2 protons, 2 neutrons. For a grand total of 4 on the bottom and 2 at the bottom, or 4 on the top and 2 on the bottom. 2 plus 2 is 4, and then 2 protons. 4. Now, what is an alpha decay? An alpha decay is a slow, large, heavy thing. And it's not very penetrating. It's not very good at shooting through stuff. You can hold an alpha emitter in your hand for a little while. It's not a big deal. Your skin will absorb most of the alpha particles. If you inhale alpha emitters, that's a big deal because your lungs will basically, they don't work like your skin does. Your skin is constantly sloughing off. So the particles are hitting your skin, killing those cells, and your cells are constantly sloughing off anyway. So alpha decay is big, heavy, and slow. And it's very easy to block. Anyone played Red Rover when you were a kid? Yeah. Alpha particles are the fat kid. Red Rover, send the fat kid over. I was the fat kid. So it was like, Red Rover, send the slow fat kid over. Red Rover, send Byers over. I'm like the alpha particle, I'm like, I can't make it. Boom. Oh well, it didn't make it, so I wasn't running very fast. Okay, that's an alpha particle. It's big, it's slow, it doesn't penetrate through materials. You can block it with paper, skin, not a big deal. One thing that it does do is it creates ions. It's ionization. Because the alpha particle has those 2 protons in the nucleus. 2 protons carry what charge? Positive 2. So what they do is they cruise along. They take electrons from atoms. Hey, the alpha particle ceases to exist, becomes helium, because it took away those 2 electrons, and whatever molecule those electrons were taken from disappears. Got it, Scott? Okay. So that's alpha particle. Any questions about alpha particles? Yeah.
Which part is positively charged again?
The protons. The protons are positive. Since there are 2 of them in the nucleus, the alpha particle carries a positive 2 charge. Other questions? Another thing we're going to be doing on Friday is balancing nuclear equations. This is a nuclear equation. What are the first 2 syllables in the word equation? Yeah, equal. It's equal. So just like in math, when there's an equal sign, whatever's on the left equals whatever's on the right. In nuclear equations, same deal. Whatever's on the left equals whatever's on the right. 92 equals 90 plus 2. 238 equals 234 plus 4. Give me a thumbs up if you can see the math. Okay. Nuclear equations are super fun because you basically just do arithmetic. Okay. That's an alpha particle. All right. Shall we move on? Question?
Why is ionization damaging?
Because when those electrons are taken away from the compound ceases to exist. Because compounds have a set number of electrons that are used to bond atoms together. And if those electrons are removed, the bond falls apart and the molecule falls apart. And we're going to get to molecules in a little bit. But basically that's what it is. So you have atom A, atom B, and they're chilling in a molecule. That molecule is useful. Alpha particle comes in, steals away the electrons that are used to bond the atoms together. The atoms bonding electrons are gone, the atom falls apart, and it's no longer useful. So realize that could happen trillions upon trillions upon trillions upon times to you and your lungs. Those cells are going to start falling apart because the proteins that make them up are going to start falling apart. That can kill you. But if you're just holding it in your hand like, well, that's, okay. You actually have radioactive material in your house. You're sitting on radioactive material. You are breathing radioactive material. Everything around you is radioactive. You cannot escape it. It's impossible. The food you eat were grown in radioactive ground. The concrete that makes up this room, the blocks of this room, came from radioactive mountains. You cannot escape radioactivity. You can't do it. It's possible. Your teeth are radioactive. The calcium that your body used to make your teeth 15 years ago, 10 years ago, that calcium was radioactive. Your teeth are radioactive. You can't escape it. It's called background radiation. It's everywhere. Background radiation. Now, if you do a lot of cave exploring, or you're a dentist, or a dental assistant, you're going to be exposed to a lot more radiation than everybody else, but still, everybody's exposed to radiation. You can't escape it. And it's not bad either. Radiation is not bad, it's just part of life. Okay, shall we move on? All right, move on. Beta decay. Beta decay. So beta decay is the athlete in our Red Rover analogy. This guy can run really fast, blast right through people. I don't know who our track stars are in here, but if that's you, you're a beta particle. You're fast, you're smaller than alpha particles, but you're also extremely fast, so you're good at penetrating things. This is the 5'8" forward, just bobbing and weaving between the guards. He's fast, he's small, he can get between things. That's a beta particle. Now, beta particles are small. They are actually high energy electrons that get ejected from the nucleus. Beta particles are high energy electrons that get ejected from the nucleus. Now, some of you should be kind of itching at that fact too. Why is that a weird statement? Exactly. How can an electron be ejected from the nucleus? There aren't any electrons in the nucleus. And it's true, there aren't any electrons in the nucleus. So how can one be ejected from the nucleus? We can brainstorm.
Yeah, when you said earlier that when it loses energy and falls into the nucleus, then it will be expelled.
That makes sense, but it's not what happened. Let me show you. Very, very simple math. A neutron has a mass of what? 1 and a charge of 0. A proton has a mass of 1 and a charge of 1. And an electron has a mass of 0 and a charge of -1. That's how. Beta particles, beta radiation happens when there are too many neutrons in the nucleus. If there are too many neutrons in the nucleus, those neutrons don't have a job, they just leave. Much like you and I. You're like, this is boring, I'm not doing anything, I'm out of here. And what happens is the neutron becomes a proton and ejects the extra energy in the form of an electron. Crazy. Now what does that mean? That means the atomic mass doesn't change, but the atomic number goes up. Because what's the atomic number? The number of protons. So if the atom just gained a proton, then the atomic number goes up and the identity changes. So like this, iodine 13153, 131 equals 131 plus 0, makes sense. 53 equals 54 plus -1. When iodine undergoes beta radiation, the iodine atom becomes a xenon because it has another proton. Crazy. Does that make sense though? Okay. Again, the protons, there's too many neutrons, neutron turns into a proton, kicks out the extra energy in the form of a high energy electron. Okay. Beta particles will travel right through you until they hit your bones. Your bones are dense enough and made mostly of metal. Your bones are made mostly of metal. Your bones are dense enough that the beta particles will hit your bones. Okay. Questions? Okay, the next one is a little dicey. The next one is gamma radiation. Gamma radiation do not get included in nuclear equations because they're spare change. They're what make the really exotic equations work that we're not doing in this class. if we had to do KeV, MeV, if we had to do energy calculations, then we would need to include gamma particles. When you take physical chemistry in college, you'll have to do that. But right now, you just need to know that gamma particles are spare change. They happen during other kind of radiation. You want to buy a taco, you have a $5 bill, you exchange your $5 bill for the taco, and there's some spare change. The spare change is the gamma particles. Gamma particles are really good for turning scientists into Incredible Hulks and students into Spider-Man. Yeah, let's try it. Everybody bring a spider. Now, if you want to block gamma particles, you're going to need something very, very dense and quite a bit of it. Because if you're going to block gamma particles, you need something like lead, something that's cheap and dense. When I was your age, I worked in a physics laboratory and over a summer. This is a really cool program called Apprenticeships in Science and Engineering. And I was an apprentice, and one of the things we did is we irradiated broccoli because the theory was that broccoli retained a lot of radiation. So we put the broccoli in what's called a pig. The pig was called a pig because it was about this big, and it's like 2.5 inches of lead with steel around the lead. And you open the pig, you put the broccoli in, then you put your radioactive source in, and you close the pig. That way, you weren't irradiating yourself or the computer you were working on while it was radiating the broccoli. Then we took the broccoli out, or then we took the radioactive source out and put our detector in and closed it, determined if the broccoli stayed radioactive. Oh, you want to know now, don't you? No, it doesn't. Broccoli does not retain radioactivity any more than any other vegetable. Yeah, darn. It's going to get superpowers. But that's what we did. That's what I did. 26 years ago? Oh my goodness. Okay, so gamma particles don't get included into nuclear equations. This is what it would look like if they did, but we're not going to worry about it. They don't change anything. Okay, summary of the first 3 basic types of beta decay, of nuclear decay. Alpha particles, they're big, they're heavy, they get blocked with tissue. Beta particles, they're high energy electrons. They will go through most low density things like skin, blood, your face. They hit your skull, they stop when they hit your skull. Gamma particles will go right through you most of the time, and they have to hit, you need something very, very dense like lead to block gamma particles. You can think of gamma particles as behaving a lot like X-rays. You know, remember when you get your dental X-rays, they put that big lead shield over you? Gamma particles work a lot like X-rays, but they're higher in energy. If you look at the electromagnetic spectrum, you'll notice X-rays are right here, and gamma rays are further over at the higher energy end of the spectrum. But they behave a lot the same. Okay. Questions? There's one more type of decay. It's neutron decay. And neutron decay is exactly what it sounds like. And it's going to make a nice little transition on Friday into nuclear reactions. Neutron decay is a high energy neutron. Here's the problem with neutron decay. It's a high energy neutron traveling pretty close to the speed of light when it leaves the atom. And a neutron is very, very massive. Imagine somebody hits you with a tennis ball. Imagine how hard that would, or how much that would hurt. Now imagine somebody shoots a tennis ball at you at 1,000 miles per hour. Imagine how much that would hurt. That's basically what's going on in neutron decay. The neutron is blasted out of the atom at extremely high speeds, and as it's going, it's hitting air and slowing down. And it's hitting air and slowing down. And it's hitting a building and slowing down. Every time it slows down, it releases a little bit of energy. And then a little bit more. And every time it hits an air molecule, it releases energy. And if you have enough of them, what do you get? A mushroom cloud. Yeah, If you get enough energy, you create so much heat release as the air heats up because the gamma part or the neutrons are slowing down that you get a mushroom cloud. This is the primary destructive force in a nuclear reaction. So this is a good place to stop. We'll pick up, I'll just finish this slide, and we'll pick up here on Friday. Questions?